Okay, excellent. So this is week 4 of 6, and here you can see we've got Saptarshi, and he'll be speaking about microseismic event detection using machine learning and Bayesian inference. So we're really excited to have Saptarshi. Those who have been joining for the past few sessions know that every Tuesday morning from 9 till 10. QR code here in case anybody needs to access the main Eventbrite pages. And then, yeah, just a little bit on Saptarshi. We've got his web address for the university there in case anyone wants to key it in and see a little bit more. But just to speak through it a little bit, obviously last week we had Jane Galway giving us an excellent presentation on machine learning techniques for remote sensing and surveying. And this week we move on to Saptarshi, who's a data scientist, interdisciplinary AI and data scientist with background in control and power engineering. Hosted in the Department of Mathematics and the Centre for Environmental Mathematics on the Penryn campus. He's really interested in dynamic systems and control theory, big data analytics, machine learning, computational intelligence, signal processing, among other things. So as I say, just to reiterate that Saptarshi's happy to take questions throughout. I will do my best to field these and pose these with correct pronunciation if we get into some real tricky pure maths terms. So please do include these in the Zoom chat box, either to the group or just privately to me if you prefer. And we'll do our very best to have these included throughout and, you know, just kind of react to the nature of the questions and the nature of Saptarshi's content. So thanks very much for listening. I will now hand over to Saptarshi. Yeah, it's looking good, Saptarshi. Just come through on full screen. Awesome.
Okay, great. Good morning, everyone. My name is Saptarshi. I'm a senior lecturer in the Department of Mathematics at the University of Exeter. I'm also the Institute for Data Science and Artificial Intelligence theme lead for the Cornwall Hub. So what I'm going to talk about today is microseismic event detection using machine learning and Bayesian inference. So this the content is about this is kind of 2 years of with some of my colleagues and other industrial collaborators in the oil and gas sector. So feel free to stop me anywhere if you have any questions. So I'll try to make it a balance between geophysical audience and relevant for industries, especially in the mining sector. So why do we care about microseismic events? It's basically mini earthquakes while you do mining activity or any sort of drilling activity. So what happens, like you get some accumulated stress in the reservoir. So it can be due to some cracks or ground movements in the reservoir, and depending on the stress accumulated, you get different levels of these small or mini earthquakes that is usually not perceivable using standard sensors. So what we are interested in estimating is how many events are happening, which is given by this NE, number of events, origin time, when did it happen, and amplitude, that means how much energy was released by this microseismic event or the mini earthquake, and if there are, and what are the process, how did it generate the energy. For example, it can be sleep or for example, like one rock layer going beneath another layer. So there can be various different ways how these cracks can develop. So that's why we have different physical parameters called moment tensors. So this is kind of a matrix, and we have this 6 components, XX, YY, ZZ, that basically represents the movement along different directions, or even the cross planes like XY, XZ, and YZ. So these are for shear sources, or one can have an explosive source. For example, if you crack something in the subsurface, so that's usually an explosive source. Otherwise, it can have a shear source when you have like landslides and that sort of stuff. So what we measure usually, especially in the oil and gas sector, so these are like 4 component seismic data. I'm assuming like in the mining sector you have similar measurements. So if it is for example, if you have a hydrophone, then you measure the pressure. If you have a ground measurement, then you have particle velocity or acceleration. So either way, so Vx, Vy, Vz. So these are the measurements. So the task is, given these measurements, what can you understand about the properties of the subsurface as well as where these cracks are forming? So the known quantities, what we employ for the modeling, this is called forward modeling. So you need to have a detailed geological model. Often it is called 3D velocity model. Which is often heterogeneous. That means you need to know that density, compressional and shear wave velocities at each grid point, and it depends on how fine the resolution of the model is. For example, you can have a it can be few meters to kilometers, so depending on the resolution of the model, the computational burden would be in different levels. Then the next bit is how much seismic noise or the background seismic noise the sensors are picking up, because no sensor will be perfect, and also there will be many different ambient seismic activities or anthropogenic activities where you get some complicated noise characteristics. So we need to, well, like when we try to understand the characteristics of these events, we need to make sure that these are not due to the unwanted noise. So the main challenges here is, while we invert these models, how do we run big computational simulations? Especially we'll need the use of graphics processing units or GPU clusters in order to be able to simulate synthetic seismic patterns. But still, this is not good enough. So we'll need machine learning surrogate models. So once we run a few different simulations, which are basically some partial differential equations with some given material properties. So you run some simulations of the reservoir, how the like from prospective source locations, how the seismic patterns will look like, and then train a surrogate model through a machine learning model to even accelerate the process faster. After that, we investigate the signal to noise ratio and whether we can detect events which are comparable to the ambient noise, because often these microseismic activities are in such a low level, like it's the amplitudes are really small. You really can't see them with naked eyes. So we need sophisticated statistical methods to understand where these are happening. And also, like the other challenges are detecting each of these events separately. So for example, how would I discriminate one event versus another? Okay, and determining the source mechanism and number of events. So these are important challenges, and also understanding how many events are there and how many are due to some spurious noise. Yeah, so how many are real and how many are non-real events which appeared just because you have more measurement noise on the sensors. So this is a part of hypothesis testing, and especially here we apply something called Bayesian statistics, which is a computational method where you can set priors, and so you have got different degrees of beliefs in your answer. So it's not a yes/no answer. You have got probabilistic arguments. So although it might be a little bit difficult for people who are not that much like people who do not use statistics too much, but the main reason is for every argument, for example, what are my amplitudes and how many events are there. So these are all probabilistic statements. So basically there are 3 steps. So given this sort of geological model, so I'm assuming that where you want to do a drilling activity or you want to monitor the reservoir or the mining field, like whether there are microseismic activities happening. So you need to have a fairly detailed model with the knowledge of density, P velocity and S velocity. and then you run some few hundreds to thousands of simulations, forward simulations from prospective locations. You don't know where they are going to develop, so you just assume certain locations and run some simulations, and then store the synthetic seismograms. Then the next step is one need to compress the information content in the seismogram, because most often you'll see the the actual information in the seismic patterns. They're located at certain temporal positions, or so the amount of information is very less as compared to the volume of the data. So we need a data compression algorithm, or extraction of features from the seismic data, and then train a machine learning model or a surrogate model that will basically try to generate the same sort of synthetic patterns from any other arbitrary location. So as I said initially, you run few hundreds to thousands of simulations with the precise governing physics or the geophysical knowledge of the model. But later on, you move to a different location. You don't need to run the same expensive model multiple times. And the main purpose of the machine learning model is whether one can try to interpolate this using a neighborhood processing. So if you just move a little bit in X or Y direction, whether you can approximate the seismic pattern or not. Yeah. And you can have different type of receiver numbers or different arrangements. You can also add noise on top of the synthetic seismic pattern, just to investigate how much noise it can, I mean, whether you can still get the right solutions even though you add a lot of noise, which is quite realistic. So this is the second step, and we particularly use Gaussian process regression, which is one of the probabilistic regression methods. So the outcomes, the regression results that you get, which is the seismic patterns, they are probabilistic in nature. So the first step is GPU-based partial differential equation solving for elastic wave propagation. So there are various ways how you can reduce the computing. So one can just consider the density and the p velocity. So that's an acoustic wave propagation equation. So there are different levels of governing physics. So elastic wave propagation is the most expensive case, where you consider all the three properties of the rock layers. And also there can be many, like for example, here you see like along X direction, or sorry, Y direction, it's symmetric. Okay, so you can reduce this three-dimensional model into a two-dimensional model. But in many cases, the layers can be quite heterogeneous. So in that case, you need the knowledge of the full cube. So with multiple, like few millions of voxels, and you need a detailed model. So in that case, you'll have more, you'll need more detailed forward geophysical modeling, and the number of samples that you need to train a reliable machine learning surrogate model will be much higher. Then the next step is Bayesian inference, which is an inversion process. So basically, given this seismic data, can I get back to the properties that I put in the physical model? That means that it could be the velocity model, like you want to know the density, PS, wave velocity, this properties, or where the sources were, and what was the type of source. So all these questions can be answered with some probabilities associated with these unknown quantities, which we call as posterior probability. So we assume certain probability distribution for each of these parameters, which are called prior probability, and then you invert this in the light of this data. So you get something called posterior probability, and you also get something called evidence for your data and the model using another method. And so these are called sampling methods, Markov chain Monte Carlo sampling, and these are part of the umbrella term called Bayesian inference or Bayesian statistics. So for more information, you can look at this paper. So I'm just trying to explain how complex this model is. So as you can see, along Y direction, this is kind of symmetry. There is not much complexity, but here along X direction, it's changing. Yeah. So the first step is, out of these 2.8 million grid points. So this is a detailed geophysical model. I've just shown 2 layers, the extreme layers in X and Y direction, but there are more complexities here. Okay. So you need to generate synthetic seismograms. So assuming that if my microseismic source is here and my receivers are located at the junction between the water body. So this is water, the blue bit, and these are different rock layers. So if I put, so it's a kind of marine environment. So you can think of it's a the sea floor is where you see the light blue color. Okay, and you're placing different receivers, like various numbers of receivers here, and assuming that if the microseismic activities happen here anywhere in this volume, how the seismic patterns will look like. This is what I'm going to record or simulate. Okay, in order to be able to calculate a likelihood function, which will be which basically matches the synthetic seismic patterns versus what I have observed from the sensors. Okay, right. So as you can see, we ran few like use 2 different GPU system. One is K20 GPU. This is from Tesla series. This is a little bit expensive as compared to a simpler GPU, like a but it depends on like, so right now there are like K40, K80 different GPUs. So if you have a better GPU, then the whole model will run faster and you'll get the results sooner. So that's the only difference. Right, so you need these many samples and store the data set somewhere to train a machine learning surrogate model. So it not only there are challenges regarding the simulations on a cluster, like on a high performance computing cluster system, but also there are additional challenges for storing the data and compressing it. So these are additional challenges that we'll need to tackle. So I'm just showing here a few cases where, for example, if you have a heterogeneous velocity model with rho is density, p and s wave velocity, and you're assuming that it happened somewhere. So these snaps are showing how the seismic patterns are evolving over time. So t equals 0.1 second to 0.2 second. As you can see, the circles are going bigger and bigger. Yeah, and after a while, all of them are mixed. So you really can't see, like you won't understand where the source is. Yeah, and it's basically looking at from a x and y direction, but we also want the z, an estimate of the z or the depth. Yeah, that's why we want to fuse multiple sensors data. So in terms of the measurements, how the acoustic pressure, the velocity along x-y direction will look like if you have a explosive event. So all of them are explosive events as they are creating this sort of circles. So the blue, the red is a negative pressure, and the black is a positive pressure. So you get a up and down. So that's basically plotted here. So these are called seismic plots. So when you have a deflection, so it's basically you have to understand it's a positive pressure or a negative pressure. Yeah, and similar for the velocity as well. But not only microseismic activity can happen because of explosive mechanism, it can also be generated due to other type of source mechanism. And this is given by this matrix called moment tensor, so or stress tensor. So in the diagonal, you have like when you just have these diagonal terms, you see these sort of circles, and this is called the explosive source. It's almost like cracking something like cracking an explosive in the subsurface. So you'll see circles, and the circles will go bigger as you move in time. You can have other type of things, for example, double couple or CLVD source, which are basically when you turn on these elements, you see different patterns. So here you see 2 blacks, and then there aren't anything here, and it gets reversed if you take a mirror image and the along this axis. So there can be various different patterns. And when you look at the seismograms, you see this is this is called the P wave, or the first wave you see like when you have a event. So, and there is a S wave or a delayed wave, which is kind of invisible in the explosive source. But for double coupled source or CLVD, you see the S wave. This is bigger, and the P wave, which travels faster, that is weaker. So there are different ways of identifying these events by looking at the seismic data sets. And it creates really complicated patterns. So I'm assuming that if you have a array of sensors employed in this uh, in the seabed, yeah. So as if you are measuring in each grid point, yeah, then you'll be able to generate this sort of plots. This is all in simulation platform. In realistic scenario, you'll have a sparse recording. So you'll employ sensors at certain locations and get the seismic data. So this is X versus Y, and the snaps are showing how it evolves in time. Okay, when you have a double couple source or compensated linear vector dipole type source. So these are different source mechanisms. And as you can see, the locations are basically the same, but the patterns have completely changed. Now the question is, if you have a more complicated geological model, for example, if you think about Cornwall or a certain location, what will happen here? Depending on the complexity of this model, these patterns will be very different. Okay, because interacting with the rock layers, the wave gets splitted. So like some part gets reflected, some part gets refracted, and the property of the wave is very much dependent on the material it goes through. So not necessarily for the same model, like for the same scale of model, if you have the same location, if you put a source, it will give you completely different patterns depending on the geological model. So the simulations are very much dependent on the geological structure. Okay. The next step is what we did here. We ran few hundreds of thousands of simulations, and then the next bit is we can't run these simulations again because these are quite expensive. So you have to run this offline. You can't run them online. But when we try to invert them, or for solving the inverse problem, you need to run similar simulations again, okay, given the measurements. So what we try to do here is, given these locations X, Y, Z, so you assume I know the precise location of the event, and then I simulate a data, which is a seismogram, as I've shown here. So it looks like one of these. So these are like vertical lines. These are basically the each of the sensors measurement or the seismograms. So we are just considering one of these lines. Okay. So that's my for prediction. Yeah. So this is the receiver location, and then what you calculate here is, given the source locations and the seismic data, whether we can try to map it using a regression model. Okay, this is where the machine learning comes in. So the idea here is, I won't be able to calculate the seismic patterns for all these voxels. So here, as you can see, for this sort of model, which is kind of 1 kilometer by 1 kilometer model, typically I have got 2.8 million grid points, these many grid points, and it's almost infeasible to run 2.8 million simulations. So what we did, we ran only a fraction of them, okay, at prospective locations. There are certain ways how you distribute these prospective locations, okay, without losing much information. But definitely you'll have to run few hundreds of simulations or thousands of simulations and then train a model. The expectation here is the machine learning model will be able to interpolate for any new query of XYZ, so that it has not seen. Okay, so we use a compression method to extract the most informative part of the seismograms. And it's a time domain decomposition method. One can also use frequency domain methods using wavelets or Fourier basis. And from this, we employ series of machine learning models. Those who are working on some of these might know the names, like polynomial regression, shrinkage methods, generalized linear model. So we found that Gaussian process, this has been the best for this particular application. Support vector machine, neural networks, ensemble methods, all these different family of machine learning models. So the role of supervised learning here is to train a proxy for the elastic wave propagator or the elastic wave equation solution without running the expensive simulation on a GPU. And this can, like this sort of supervised learning models won't need a GPU simulation at all. So you can run it on a standard computer. If you have multiple cores, even the small, like standard laptops will have 4 cores. So you can train supervised learning algorithms on a kind of cheap hardware. The advantage here is you won't need the GPUs, and the runtime is pretty fast, although it will not be very accurate. But we can tune this. For example, if we want a criteria like the R or the correlation coefficient between the original versus the reconstructed data is greater than 0.9, so that means we are getting fairly accurate seismograms, and I'll show you in the coming slides that these methods will give you pretty accurate results. Yeah, and you can change the machine learning models to get something around this straight line. So just to show you here, like the patterns you get look something like this, but actual information lies only in this surface. And when you use the compression method, you can approximate this, although there are some aberrations, but it's pretty accurate. So that when we try to reconstruct it, so I've just shown a couple of graphs. So the blue dots are basically the original ones, and the red ones are the reconstructed ones. And when you superimpose both of them, you can barely distinguish them. So you can see the Gaussian process regression model is pretty good to approximate the original seismograms. And not only it is just for a single location. Yeah. So if you have multiple sensors, so this is the ground truth. So we just took random samples, 400, 800, all these samples, and then using a Gaussian process with the different basis functions, which are some hyperparameters. Unless you are into Gaussian process regression, you don't need to care about these two things. But the important bit here is to note these numbers. So this R, or the correlation coefficient, is pretty high, and there is almost no difference between this one and that one. Okay, so all of them are pretty accurate. Right.
Saptarshi, can I jump in?
Yes, please.
We've had a question appear in the chat now that's relevant to the Gaussian processes. And it says, fascinating presentation, Dr. Daz. How do you get a Gaussian process to run with 2.8 million data points? GPs are known to be incredibly computationally expensive. Yeah, that's the reason we don't run on 2.8 million data points. That's the number of data points in the geological model. So here we just take a few hundreds or thousands of them. I ran 4,000 simulations and splitted the data into 2 halves. So 2,000 data points for training the model, and rest 2,000 for testing. Brilliant. Thanks for clarifying that, Saptarshi. I know you mentioned that earlier in the presentation, but it's really good to underline that point. And to extend it a little further, the question goes on. Also, what pleases the advantage of Gaussian processes over other machine learning methods? Further, what is the advantage of Gaussian processes over more conventional geophysical inversion algorithms, say linear or quadratic programming? Here we are not we haven't gone to the inversion
part yet. Okay, what we are trying to do here is the data generation process, which is through a partial differential equation solving or a geophysical model. So you have a geometry, and then you have all detailed in models of the material properties, yeah, and you set up the governing equations and boundary conditions, everything, and you generate the data from the geophysical simulation. Now, what we are trying to do here is we are using Gaussian process to give us accurate approximation or the surrogate accurate approximation of the geophysical data generation process. So that's what it is doing. Yeah. So so if you use any other, for example, like neural network, I'll share the results. Neural networks are pretty close to Gaussian process because there are similarities, but the other methods are pretty useless because the complexity of the data generation process is very high because the material is heterogeneous. As you can see here, you have to approximate the whole wave field, yeah, x, y, and t um, for all grid points. It's pretty hard job, and that's the reason the simpler machine learning algorithms won't be able to do a good job here. And you need a flexible basis function. So the short answer is Gaussian processes are incredibly flexible, um, um, and also like neural networks are similar, um, and that's why these two algorithms typically wins over many other methods.
Awesome. Thanks a lot for the clarity, Saptarshi. We'll let you move on. That's brilliant. And do keep the questions coming if anybody wants to bring something out of this.
All right. So the whole purpose here is not only we get very accurate seismic responses, but also the runtime becomes pretty fast. You can see on the expensive, like full geophysical simulation on a K20 GPU card, it takes 20 minutes around. And if you rather generate it through a machine learning proxy or a surrogate model, it becomes 3 seconds. So 20 minutes to 3 seconds, that's pretty fast. Now, then, so like this trained model can be used for the inversion process because you really can't afford to run 20 minutes multiplied by few thousands of simulations, but you can afford 3 seconds multiplied by few thousands of simulations, which is through the machine learning proxy. So the next slide shows, do we really need to run few thousands, or few hundreds are fine because these are like expensive computational simulations? So how many simulations do we really need? So this can be answered through a learning curve, and as I said, it all depends on the complexity of the geological model. So this shows like when you start from sample like 10 samples, 100, 20, 100, few like 100, 200, as you keep on increasing, so there will be you expect less difference between the training set and the testing set. So that's the reason why generating few or like whatever many samples you want, you can afford to simulate, split it into two halves, and then see what's the difference between my percentage accuracy for the training set and the test set. Okay, using different kernels here, we see they're almost converging, and we can cut anywhere here. So 1000 samples perhaps it's fine for this particular model. Okay, but if you change the model, if the heterogeneity of the geological models becomes like higher, so you might need even more than 2000. What's the kind of runtime here? 500, 600 seconds if you change the kernel, but all of them are pretty accurate, as you can see from the R-square, or the coefficient of determination, which is the degree of agreement between the simulated data through the proxy and the original GPU simulation with all governing physics in it. Now, moving to the inverse problem. So first we'll try maximum likelihood inversion. So after we have got the data, so this is, for example, we have got this data from the sensors. So just assume that you're looking from the top as if, and this is the ocean bed, yeah, and you have got these are the sensors. Although you are running the simulation on all grid points, so you have the data at every single grid location, yeah, but you are just distributing the sensors at certain locations, and you can create certain geometries. What happens if I take only the principal diagonal or off diagonal or the upper triangular part, lower triangular part, or all the 23 receivers? So I'll show you. If we take different, if we leave certain group of receivers, what sort of results do we get? So these are the original data, noise-free seismogram, and then we add some synthetic noise. So sigma becomes 100 or 250. So here you see, like in the rest of the part, you have got more noise. And from 7 to 23 receivers, you have got different arrangements. So the whole idea here is, if we try to use these data sets to estimate the properties of the seismic events, how accurate do we get? So we are trying to estimate the X, Y, and Z locations here. So as you can see, when we take the central, just this sensor, a single sensor, and try to estimate that, you get many spurious results. So black is saying, like black is the likelihood value, which is saying here is an event, there is another event, but actually there is a single event that you simulated. But since you are using just one sensor's data, it is showing you many spurious events. But things gets better when you fuse more number of receivers data. So if we take the principal diagonal, 7 sensors, you see like rest of them has got a lighter color. That means these are not meaningful. The strongest evidence is here. Okay, and as you move in the right side, like when you fuse all the sensors data, you see the prominent one is here in the 3-dimensional case, like X, Y, Z. Or if you look at the plan view or from the top, you see this one is definitely a microseismic event. These are some spurious cases which you are getting because of the noise. So definitely this noise will appear as some spurious events, but there you can always discriminate between the real one and the spurious ones. Right. So the comparison between true and surrogate-based likelihood calculation. So if you can afford, as I said, like initially few thousands of simulation, you can generate a likelihood profile like this. And sorry, this one, the top panel for all these sensor arrangements. Then using the proxy or the surrogate model, you get a close approximation, although there will be a little bit of a difference. But when you take difference of these, you get pretty small number, and this works pretty well. Next, coming to the Bayesian inversion or Bayesian inference, so to say, a little bit of math. So here, so theta. So theta is basically the properties that we are interested in for the microseismic event. So L theta is the likelihood, pi theta is the prior or the some prior knowledge. So we can assume a uniform distribution or a Gaussian distribution here. This is normalized by evidence, and what we get in the left-hand side is called the posterior distribution for the parameters that we are interested in estimating. And there is another parameter called marginal likelihood. This is particularly useful for hypothesis testing. How do we discriminate between the real event versus the false events? So we here assume a Gaussian likelihood. So Y is my measured data, which can have noise and all that stuff. And Y hat, that is the simulated data through the proxy, and which is pretty fast to generate right now. So we calculate the likelihood like this, and also estimate the noise covariance that should go here. Okay, the C inverse term. And then you can think of like MCMC or nested sampling. These are kind of black box that will throw some samples through the proxy, and it will give you the posterior probability of the parameters that you are interested in. So I'll not go into too much detail of this. I'll directly go to the some of the pictures. So for example, if you have a little bit of noise versus a lot of noise, okay, as you can see, the signal to noise ratio here is quite high, 12, and here it is negative. That means you have got more noise as compared to the data. So the blue is the data, and you have got more noise here. So if we use an inversion, a Bayesian inversion technique, you get a posterior probability. So we are trying to estimate the X, Y, Z locations. So the diagonal is the marginal distributions, one-dimensional marginal distributions. And here you have got the kernel density estimate for X and Y, XZ, YZ, like that. So when you have more noise, the variance of this will be higher, but this is the true location. It will still be able to identify the right location depending on how many sensors data you are fusing. So here, if you use just a single sensors data, it will not be that accurate. If you use more sensors, then definitely you'll get a better estimate. Then the full posterior inversion can be done using different ways. So the raw seismic data, that is definitely more expensive. In many standard literature, you'll see like one of the questions, Shay, you were asking like what happens with the standard geophysical inversion method. So this is typically done through the second column, which is called arrival time. So you assume like a source is at a certain grid point and you have a sensor arrangement, and then one can calculate the arrival time. But the problem with this approach is you don't you neglect certain aspects of the geophysics while the wave propagation physics, yeah, that is only captured in the raw seismic data. But definitely arrival time is much faster. One can also use root mean square or peak to peak. There are different inversion methods. These are somewhat accurate, but nothing like the raw seismic data-based inversion. But the problem here is it is more computationally expensive. Yeah. So using the raw seismic data versus arrival time, if you look at the posterior distributions, you'll see you get a lot of these black patches and different colors. That means the variance is higher, but here it's much narrower. Okay, and it can get to the some of the parameters are really accurate, even though if you use just a single census data. Now I'll show you what's the role of evidence calculation in identifying true versus false events. So seismic data with no events, it's full of noise. Okay, it's just noise on the top. So you might it might seem apparently that there are many microseismic events, but actually these are all ambient noise. And here you have got some seismic activities going on, and on top of that you have got some noise. So these two models we are trying to compare. So we'll create two different models, MN, which is a noise model, which is a Gaussian distribution, zero mean and sigma square is a variance. And then another model, signal plus noise, which is FXYZ. That means it's a microseismic active pattern. And on top of that, you add some noise. Okay. And H1 versus H0. So these two models you are trying to compare given the same data. So you feed the same data and ask the question whether there is an event or not. And that is typically done through this this factor called Bayes factor, and one can calculate this using the evidence or the denominator of the equation I showed you. So this is called the Bayes theorem. So the denominator of the Bayes theorem helps you to do this sort of hypothesis testing in a Bayesian way, where you fuse all the models and the data together. Right. So here it is showing, it is fluctuating for the case where you have you're showing only noise when you have a single data. Okay, you have a single microseismic activity going on, even though you have got a lot of noise, sigma equals 900, something like that. So where your signal to noise ratio is going below zero, so anything above zero is visible with naked eyes, but even though you have got more noise as compared to the event, you can still detect it, because it might seem counterintuitive, but actually it is happening because the noise will cancel each other while you fuse the sensors, like multiple sensors data. If you use a single sensors data, then definitely it's going to be less accurate. But not only you can get an estimate of the XYZ, you can also get an estimate of the A0, which is the amplitude of the seismic event, and T0, like when did it start, when the mini earthquake happened. Okay, so that is basically the T0. So it's a 5-dimensional case that you can simulate and invert it with a noisy seismic data. Yeah, this shows you the computing time, which are in terms of few seconds to minutes, not very expensive. Thanks to the proxy or the surrogate model, this can only be possible once you train a neural network or Gaussian process-based proxy to be able to apply this sort of methods. Otherwise, like if you want to solve the full partial differential equations few thousands of times, it's infeasible. So here there is a search parameter, resolution parameter called nlife, which is specific to the method called nested sampling, which is a different version of Markov chain Monte Carlo sampling. I won't go into too much detail of this. I just wanted to focus on the pictures, which are of more relevance. So when you have like no noise versus a little bit of noise versus a lot of noise. So when you see like signal to noise ratio 0.65, you can still see the patterns, but here it's very confusing. Next, I'll show you like in the Bayesian methods, there is a big role of choice of the prior distribution. So here we assume that XYZ, or the location of the event, lies between 1 to 81, so or 1 to 243 in the depth. So these are the grid locations of the voxel numbers. Okay, but these are discrete. But these like amplitude and the time, they can be so amplitude can be continuous, so it can take fractions. Time can also be fraction. Okay, so this is the ranges, and we are assuming that here all the prior distributions are uniform, so that means it's flat. So there is the like the event can happen in 1 as well as in 81 with equal probability, but you can have different probability distributions, and I'll show you how things gets changed. So with unequal amplitudes, if we assume 3 different events with different amplitudes, you can get the inversion result. So these blue dots are the true locations, and when you run the sampling algorithm, it will start from random location, but it will quickly navigate towards the original locations. Yeah, so these blue dots are the real locations, and you can see like from the random points, it will make its own way towards the high density regions, and then you can visualize this in terms of the posterior distributions like this, where you have the marginal distributions along the principal diagonal, and then the kernel density estimates and the scatter plots like this. So what did we achieve? First thing is establishing that superior, like the full seismic waveform based inversion methods are superior as compared to arrival time picking and many other, like even in highly noisy background. So simply the arrival time based method won't work if you have negative size signal to noise ratio, something like that. And yeah, which is called below noise floor. Most of the methods won't work, but the full seismic wave based inversion methods are much better. You can carry out hypothesis testing using the Bayesian evidence, but evidence calculation using standard sampling algorithms are expensive. So you have to use some clever methods called nested sampling. Then microseismic event location, origin time, amplitude parameter inference can be done, all of them together. One might not be interested in some of the parameters, so then we marginalize the distribution, because the results are basically probability distributions in multiple dimensions. So the rest of the stuff you can neglect or marginalize. You can just sum it over the interested domains. Okay, but the whole idea here is we are creating template seismic simulations and using that in the search process rather than a blind search method, which is mostly done in the standard machine learning algorithm. So this is more about physics guided machine learning, where you incorporate the physics inside the machine learning algorithms rather than just showing it a lot of data and trying and expecting that the machine learning algorithm will pick up the complexity of the data. Next, I'll show quickly. I think, yeah. If we change the prior distribution, previously we chose an uniform distribution. So we can also try exponential prior for the amplitude, because there are usually a lot of low amplitude events, and then high amplitude events are rare. So this is called maximum entropy prior. So if you change that, and if you have more number of events, so these parallel lines are basically showing how many events are there. And one can run clustering algorithm on this to understand how many events are there. Yeah, so I've shown results for 10 events, and once you run clustering algorithms, here we have used several clustering algorithms and found that something called dbScan density-based clustering works the best. So these blue dots are the real locations, and it will allow you to scoop out each of these events separately and show the posterior distributions for each of these events. And the black ones, these black dots, are basically the noise. So this particular clustering algorithm will also reject the noise and will help you to estimate the true properties of each event separately. Okay, when the data has got 3 superimposed events. And we also show, like, if you change the hyperparameters of the clustering algorithm, the results are kind of similar. It will not change much. This is the last slide. So as I said, this is a kind of ongoing project. So we have published quite a few number of papers, and you'll get the, I've shown them in the references. So in terms of practically realizing this, how much computing is really required, the biggest hurdle is the memory requirement. So for 5 minutes of data, these many samples, and you can see like how much data do you feed in the sensors. So depending on the number of sensors and how long these seismic recordings are and how big the geological models are. So these are all some concerns before we try to train the model. But the results you get is a 10D Bayesian inference. One can try that for a different type of source mechanism, not necessarily explosive source mechanism, and also try to fuse all the measurements. So the results I showed, which were particularly based on the acoustic pressure. So you can also incorporate the acceleration of the velocity data, 3-component velocity data, from multiple sensor arrangements, some in the surface seismic data or downhole seismic data, and also try to estimate the spatial temporal structure of the noise. That will even make the sampling algorithm faster and more accurate. Thank you for listening. If you have any question, happy to discuss.
Brilliant. Thanks, Saptarshi. We'll go straight into a question. It says, great talk. Thank you, Saptarshi. Sorry if I missed it, but how are you building your initial velocity model inputs for the forward modeling? Have you had issues with it being too simple or equally too complex?
Yes. So typically for the oil and gas sectors, they already give, like, when it comes to the, sorry for the noise, I think.
No problem, Saptarshi. Just, brilliant. That was,
yeah.
Is everything okay there?
So.
As long as you're okay and nothing's on fire.
Just
okay, brilliant. I'll hand back over to you, Saptarshi.
Yeah. So yeah, that is fine. Thanks for the question. So here, depending on the application, for example, in oil and gas sector, when you're analyzing this reservoir, that means there are some important stuff. Okay, so that you already know that there are some minerals or something like that you are interested in, and that's why you are studying this. So typically the first part is building this geological model. That typically comes from the surface seismic, and then you invert this. So there are methods called full waveform inversion to get this model. This is different from seismic monitoring. So what I presented is after you have this model, geological model, then how do you detect this? But definitely, like here you can have both of them in the same generalized Bayesian inference framework, where you have uncertain velocity model and also the location or the parameters of the sources are uncertain. So you can invert both of them together.
Brilliant. Okay, that's really, really interesting. I just wanted to ping over to another one we received privately. Can this method be extended for geophysical fluid flow problems or reservoir monitoring during mining or mineral extraction?
Potentially, yes. So the governing equations here are elastic wave propagation. You can have also complex like geophysical fluid flow equations. So you can just replace the governing partial differential equations from wave propagation to fluid flow problems and monitor similar stuff like when you're injecting high pressure fluid and you have a porous structure or some cracks, and then the fluid goes inside and then comes out from the other sides, or create some you get more cracks, like, and you want to monitor how the cracks are propagating in the subsurface. So all these things can be simulated, but again, given that we have sufficient knowledge of the geological structure. So here you need to know the density PS wave velocities. In the petrophysical case, you need to know the porosity, permeability, these sort of parameters, and there are ways of estimating it also. Does that answer the question, Shay?
Yeah, I think so. Absolutely, Saptarshi. They'll have the opportunity to obviously throw something into the comments there if they'd like it, the answer extended, but certainly to the previous question, they're really happy with that. So I think we'll just close there, Saptarshi.
All right.
Thanks ever so much for your presentation. Just remains with me to say thank you for everybody who attended and everybody working behind the scenes to make these events happen. I'll just flag up our contact details there. Saptarshi is one of the academics working on this project additionally. So if you want to explore some of the SME assist, some of the business assist options, or accessing the grant fund with some of the ideas that Saptarshi's proposed, get in contact with us. There's numerous means there. Email is a great option. But yeah, thanks again, Saptarshi. Thank you so much for joining.
Thanks so much. I'll be very